Ionic bonds actually result from the transfer of electrons. Um, we spent quite a bit of time already when we were looking at the periodic table trying to understand whether an atom is likely to lose electrons or gain electrons in order to become more stable. So we were already looking at ions. Remember the elements that tend to lose electrons, the metals, they form positive ions that we called cations. And the nonmetals, the ones that need just a few electrons to finish their valence shell, they gain electrons and they form anions. When we looked at that in the previous chapter, we were looking at them very independently, as if an atom could just randomly drop electrons or go out into the world and look for them and find them. And that isn't the case at all. What actually has to happen is we need to have one element that is willing to give away electrons with one that is wanting to gain electrons. So when we look at ionic bonds, what we are looking at are chemical reactions happening between the givers of electrons, the metals, and the takers of electrons, the nonmetals. Because by forming these ions, by giving away or gaining electrons, these oppositely charged ions then are attracted to each other. So ionic bonds are actually the force of attraction between positive and negative ions. We've used sodium chloride as an example before, and I'm going to continue to use it because it's such a simple, clear example. Sodium is an alkali metal with one valence electron. Chlorine is a halogen with 7 valence electrons. So if we look down here, it kind of shows us what happens. The sodium is able to lose its electron because the chlorine gains that electron. Once that has happened, the sodium, now minus an electron, has become a positive ion, and the chlorine, with its extra electron that it just gained, has become a negative, and the two then attract to each other, forming an ionic bond. So when there are ionic bonds, the compound that is formed is called an ionic compound. Ionic bonds don't form just between one single ion and another, but ionic bonds actually form in all directions. So any oppositely charged ion that is nearby will be attracted and there will be an ionic bond. As I mentioned before, these bonds are happening when we have a nonmetal that wants to gain and a metal that wants to lose. Because each of these atoms has actually achieved what they want, that valence shell that is full, ionic compounds are very, very stable. They're made up of ions that are now much more stable than what the parent atoms were in the first place. Ionic compounds are generically called salts. And if you think about what salt looks like in your kitchen, that's a specific example, sodium chloride, of an ionic compound. But it also shows you what they often look like. Most ionic compounds are actually white crystals. They're all crystals, but most of them are white. And because of this opposite attraction holding them together, and the fact that that is a very, very strong bond, we have crystals that are very, very strong and hard. And additionally, they tend to have very, very high melting points because these bonds are so, so strong. What the crystal is going to look like is going to always depend on how many positive and negative ions are a part of the formula of the compound that is made. So it would be the ratio of positive to negative that will ultimately determine the size and the shape of these crystals. So we looked at sodium chloride, where sodium has just one electron to get rid of, and chlorine has just one to gain. But it doesn't have to be a 1-to-1 ratio. If you take a look at this, we have magnesium, which is an alkaline earth metal. So it has its 2 valence electrons that it wants to get rid of, right? So if magnesium comes close enough and collides usually with a chlorine atom, that chlorine atom can take away 1 valence electron in order to complete its valence shell. But that magnesium atom would not be satisfied with getting rid of only 1 valence electron. So it would actually need to collide with another chlorine in order to get rid of that second valence electron. So each chlorine can only take 1 electron because that's all the more space it has in its valence shell. But magnesium has 2 to get rid of. So what we see is that we have this ratio. We need 1 magnesium for every 2 chlorine, because the magnesium is needing to form a positive 2 ion, but each chloride ion is only a negative 1. So you can see from this, we will not necessarily have just a 1-to-1 ratio of positive to negative every time. In this case, we have 1 positive and 2 negatives. And that also affects then what their structure looks like. This is sodium chloride up here in the upper left. For every 1 sodium ion, there is attracted to it in every direction a chloride ion. And what that begins to form is this nice cubic shape. But you can see down here, and it's a little harder to tell the 3-dimensional shape of it, but you can see that every magnesium ion is actually attracted to 2 chloride ions in each direction, and so it starts to become a much more complicated crystal. So what are they like? Well, I already mentioned ionic compounds form crystals. This overall 3-dimensional arrangement of the ions becomes a crystalline structure. And the bonds that have formed are extremely hard. They're very strong. And so these compounds will have high melting points. It would take a lot of energy put in order to cause these things to melt. So not only are they hard, they tend to be brittle, which means that when you tap on them, they're going to probably break and shatter. They're not going to break in straight lines. They're going to be jagged. They are, because they have charged particles in them, they will dissolve in water, because water is polar. Remember that from covalent compounds. It has a slight positive and a slight negative end to it, which means it's going to attract those positive and negative ions and pull them apart. So ionic compounds will dissolve in water. And when they dissolve in water, those ions become free moving, which makes them good conductors of electricity. So salt water is actually a really good conductor of electricity, much better than just regular water. Ionic compounds won't conduct electricity in their solid form because those ions are stuck in place. The bonds haven't been broken, and so they're not free to move. When they are dissolved in water and they are freely moving, they carry an electric current. That also happens when they're molten, meaning when they have melted. Of course, that would happen only at a very, very high temperature because they have such high melting points. So we're going to take a look at writing formulas for binary ionic compounds, looking at how they go together. So you'll be given the name of the compound, and then you'll have to write a formula. So to do that, you're going to first write the symbol for the metal. That would be the positive ion, and it will be named first, followed by the symbol and the charge of the anion, the non-metal. So each of those will have their charge in their upper right-hand corner. You then take those charges and you crisscross them. That means they come down and they go to the other element. And as you do that, you get rid of the positive and the negative. What this does is it makes the overall charge of the ionic compound 0. The positive and negative have to balance out. Once you have done this, if the subscripts are common multiples, then you would reduce. So if we take a look at the top left here, when lithium combines with oxygen, it's called lithium oxide. The lithium is written Li with its +1 charge. The oxygen is written as O with its -2 charge. I know the charges because of their position on the table. I take the 1 from the lithium and give it to the oxygen, and 1s are not written as subscripts, so it disappears. I take the 2 from the oxygen and cross it down to become the subscript with the lithium, and the negative sign disappears. So Li, subscript of 2, O is the formula for lithium oxide. Now, if you think about why that works, we'd have 2 +1 lithium ions balancing 1 -2. So a +2 and a -2, which of course when they add together would give us a total of 0 charge. Ionic compounds are always neutral. Aluminum oxide, aluminum is a +3, oxygen is a -2, crisscross, and we get Al2O3. So we have 2 +3s, that's a +6. We have 3 -2s, that's a -6. +3 and +6 and -6 add up to 0. So this has worked. Magnesium oxide, magnesium is a +2, oxygen is a -2, crisscross, and we get Mg2O2. This is an example of having common multiples, so we would reduce that, and the correct formula then is MgO, not Mg2O2. When we name them, that would be if you're given the formula and you have to come up with a name, you first name the metal. If there are multiple charges, multiple oxidation numbers for that metal, then we will have to use a Roman numeral. We'll talk more about that. Then we name the non-metal and change the ending to IDE, just like you did in naming covalent compounds. So BaI2 is named barium iodide. Cobalt is one of the transition metals that has multiple oxidation numbers. If you look at cobalt, it has the charge of +2 or +3 on the table, which means that it can do either. So we would have to figure out what charge we're talking about here. Cobalt would need a Roman numeral. So we can undo the crisscross. That's the easiest way to figure it out. I would take the 2 from the chlorine and go back and give it to the cobalt. So that makes this cobalt, Roman numeral 2. Chlorine becomes chloride. So as we deal with those transition metals, I already mentioned we can undo the crisscross. When you see Roman numerals, an I is a 1, II is a 2, I is a 3, IV is a 4, V is a 5, and VI is a 6. So if we are undoing the crisscross, FeCl3, we would take that 3 and give it back to the iron, becomes iron 3 chloride. FeCl2, undo the crisscross and give the 2 back to the iron, becomes iron 2 chloride.